Okay, so today I wanted to continue talking about Shor's algorithm. So I would like to take these two boxes and open them up, see what's inside, how to put those things together, and to kind of count, roughly speaking, how many gates are involved in Shor's algorithm. And you remember also the analysis that we did yesterday was specialized to the unrealistic case where the period, so what we're supposed to do is to find the minimum r such that x to the r is equal to 1, right? The period of this function or the order of the element x. And we specialized yesterday to the special case where r divides 2 to the n. There's n. Okay, let's just say there's n qubits here. And we'll have to go beyond that special case to see what happens. And I'm not going to do that in detail, but I kind of give you the bottom line of what happens. OK? So everyone on board with this? OK. So the first thing I want to do is go through this modular exponentiation. So this is just a classical step, but it has to be done with quantum circuitry because we're doing it in superposition, right? At this point, we have a superposition over all possible values of the exponent a. So how are we going to do that in a reasonable amount of time? I mean, after all, a can be as large as 2 to the little n, right? Which is quite large. And so we don't actually want to have to multiply 2 to the little n times. That would be way too many. But there's a convenient thing, which is that we can do powers of 2 very easily, right? We can make x squared. That's no problem. That's one multiplication. And x to the 4th, we can just multiply x squared by x squared. And x to the 8th, multiply x to the 4th by x to the 4th. And we've only done 3 multiplications so far, right? Even though we've gotten to x to the 8th, and so on. So that's going to simplify the whole thing. So what do we do is we break it down. First of all, we're going to write a and its binary representation to the n minus 1 minus I. So a0 is the most significant bit, the first bit if you write the binary expansion, and a n minus 1 is the last bit, the ones bit. And so one thing that we can do classically is that squaring, right? So we can classically pre-compute well, x we know, but we also get x squared, x to the 4th, x to the 8th, and so on, up to x to the 2 to the n minus 1. And now nothing bad happens if you do this using quantum circuitry. But this we can just have sitting around this classical information. We don't need to do it quantum mechanically. So we might as well kind of push it into the classical part. And we can use these values. And this is all mod n, big N. And we can use these values then actually to develop the quantum circuit. So we can figure out what quantum gates we need based on these numbers. And so here's the part that does have to be quantum. So we have the two registers. The first register is A at this point. The second register is 0. And we map that to A x to the A sub n minus 1. X squared to the A sub n minus 2. And then dot, dot, dot. no, I'll do the next one, x to the fourth to the a n minus 3, dot, 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 x to the 2 to the n minus 1 to the a 0. OK? And so these numbers are just these things. So but each of these exponents a whatever is a bit, right? It's either 0 or 1. So really all I'm saying, what we do here is say to fill in this one, we say it's some controlled, basically some controlled knots, right? And we'll do a controlled knot whenever x to the fourth has a non-zero bit. This each of these things is going to be longer than 1 bit long, right? Because it's a number mod big N. And so whenever x to the fourth has a bit 1, we're going to do a controlled knot from the corresponding bit of from a n minus 3 to that location in this register, right? And then if a n minus 3 is 0, nothing happens. We get all zeros. And if a n minus 3 is 1, we get x to the fourth. That's what we want. Okay? And so we do that for each of these. Then it's just a matter of multiplying all of these things together. And when we do that, we're going to get a x to the n minus 1 plus 2 a n minus 2. That's what we have here. Plus 4 a n minus 3 plus dot, 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 plus 2 to the n minus 1 a 0. And then we have some scratch bits that are here that we can then erase, right, uncompute them. Although, yeah, I guess we do need to do that. And this thing here, of course, is just a, right? So then when we uncompute the scratch bits, maybe I should put that on a new line. We're left with a, x to the a, and then zeros for the scratch. OK? Does that make sense to everyone? OK, so how many steps does this take? So this pre-computation step, well, every time we go up, we're just multiplying. We're just doing one multiplication, right, of this times this to get x to the 8th, and so on, right? And there's n minus 1 such things. So we have n minus 1 multiplications. Here. And so this step, each of these is basically an addition, right? We're adding, x here conditioned on something, and how many bits are in each of these registers? Well, let's see. Do I want to calculate it? Yeah. OK. So let's not count that yet. So there's little n of these additions, and then we have to do them again to uncompute. So that's 2n additions. And then this step here, we're multiplying n things together to get this, right? So that's n minus 1 multiplications. Right. So it's worth noting that because unless A is all ones, the binary representation of A is all ones, some of these things will be 1, right? They'll be, they'll be x to the, what did I say? X to the 0 should be 1. OK, so when I said we're doing the controlled knots, obviously we're not starting from 0. We're starting from yeah, I guess you have to do something a little bit different than a complete addition. It's 1 if we don't have it, and it's this if we do have it. So if we do have it, we want to start with 1 and then add this minus 1. Right. So it's still an addition, but it's slightly different from what I said. But it's very close. Anyway, the point is that if some of these bits are 0, then that term in the multiplication is just multiplying by 1, right? So it's trivial. We could skip it. But the problem is we're doing this in superposition. We don't know which bits are 0. And in different branches of superposition, different ones will be 0. So we really should do the whole multiplication kind of all the time for those segments of it that are non-trivial. OK, so we have n-1 multiplications. And another n-1 here. So that's n-1 classical, n-1 quantum. And 2n additions. So how long do these things take? So multiplication takes O of log squared n steps. And you can reduce this. If you're clever. There's fast multiplication algorithms known. But let me just start with this. And addition is easier than that. It's going to take order log n time, I think. It's the carries that make it a little more complicated. But it's certainly no more than multiplication. And so the upshot is that we have O of n arithmetic operations times O of log squared n gates per operation. So that's a total of n log squared big N. And log big N is going to be, little n is going to be order log n, log big N. So this is going to be O of log n cubed. And I haven't shown you why that's the right size for n yet. And that comes when we talk about the imperfect case where the order doesn't divide 2 to the n. But this is the actual answer. OK? Now, I said you can do faster multiplications. And so if you do that, then I guess the best fast multiplication algorithms give you something like this, n squared log little n log little n, where little n here is log of big N. OK? So the thing is that these really fast multiplication algorithms, it depends on how big a number you're trying to factor. If you're trying to factor really, 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 really huge numbers, then it gets down to this. If it's just kind of things of more realistic size, you can definitely get it below this, but not all the way down to here. It's not worth the extra effort. OK? Any questions about this? Yeah.
How can we do multiplications quantum mechanically?
How can we do multiplications quantum mechanically? Well, you know how to do multiplication classically. And so we know how to convert those classical things into reversible gates, right, by keeping scratch bits if necessary and erasing them afterwards. And so then we just do those with quantum gates, those reversible classical gates with quantum gates. But you do have to break it down into individual gates, and I mean it's an exercise to do that. It's not terribly hard, but it does get a little complicated, particularly since we're doing it mod big N. Okay. Any other questions? Okay. So then let's move on and do the Fourier transform. So unlike the modular exponentiation, this is a really quantum operation. Obviously, there's classical Fourier transforms. But the thing is that the classical Fourier transform, you're not doing it on superpositions. You're doing it. So in this case, we're doing the Fourier transform on the vector of amplitudes, basically. Whereas classically, you might have some really big vector just in your registers, and you're doing a Fourier transform on that. So classically, what you're looking for the Fourier transform is something that's polynomial, and hopefully a small polynomial, in the number of entries in your function. But here we're looking for something, but in this case, the number of entries of the function is the number of different amplitudes, right, which is 2 to the little n. And so here we want to do a Fourier transform that's something that's polynomial in little n. So it's polynomial in the log of the number of entries. So that's a significant difference from what's going on classically. And it means that we really have to involve quantum gates in this. We can't just do one of these things where we take some classical algorithm and put kets around it. Although if you are familiar with classical fast Fourier transforms, this does have a lot of relationship to that. OK, anyway, so the thing we're trying to calculate is this. So it acts on a basis state A, and it gives us sum over b omega to the AB b. And again, we're going to write A and B in binary. So let me just write them out in this case. It'll be a little more helpful later. OK, so what we're going to need to calculate is this product AB and stick it somehow into the exponent. And let's say, I guess, omega is e to the 2 pi I over 2 to the n. So what is AB equal to in terms of this binary expansion? Well, when you multiply this term by this term, we'll get a0, b0, 2 to the 2n minus 2. 2 to the 2n minus 2. And the thing is that if there's a power of 2 that's greater than n, or greater than or equal to n, it's not going to have any effect, because omega to the 2 to the n is 1. Right? So when we take this product, we're going to get 2 to the n times something, but we don't really care what that is. Right? That will not have any effect at all on our state. So let's just ignore that part and focus on the terms that are 2 to the n minus 1 or less. So basically, I'm again taking the binary expansion of A times B, and I want to write it out explicitly in terms of the binary expansion of A and binary expansion of B, because that's going to be helpful in the next step. Yeah?
Sorry, the omega is e to the power 2 to the power. I can't read the.
Sorry, this is 2 pi I over 2 to the n.
Oh, I see. OK.
Right, because we're doing the Fourier transform mod 2 to the n. OK, so what is this 2 to the n minus 1 term? Well, we could take a0, 2 to the n minus 1, and multiply it by b n minus 1. Or we could take a1, 2 to the n minus 2, and multiply it by bn minus 2, or so on, down all the way to a n minus 1, b0. And then we have the 2 to the n minus 2 term, which has, well, we can't start with a0 anymore because that's already a power of 2 to the n minus 1. So we could start with a1. It could be a1 times bn minus 1. And go all the way down to a n minus 1 times b1. And then we keep going like this. And then our last term is the 2 to the 0 power, which doesn't really have any power of 2. And that we just get the ones bits, the a n minus 1, b n minus 1. OK? That's pretty straightforward, hopefully. OK, so then what does this mean when we look at this thing here, sum of omega ab applied to b? So it's going to turn out that it's helpful to write b in kind of reverse order. So we're going to put the smallest bit, the bn minus 1 bit, first. And then, so what's going to happen in our Fourier transform when we do it is that a is going to go in normal order, in the usual order, and then b is going to come out in reverse order. But it's still calculating the Fourier transform. If if it really bothers you, you can add some extra step that switches all the bits, switches the order of them. So what I have here that I want is omega to the ab, bn minus 1, bn minus 2, dot, 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 b0. OK, so what does this look like? So let's take out the bn minus 1 terms from this sum. OK, what do we have? Well, we have a0, 2 to the n minus 1. And we have a1, 2 to the n minus 2. And a2, 2 to the n minus 3, and so on. So, well, we'll certainly have a sum over bn minus 1, because we're summing over all of b. And let's write that. We have a0, 2 to the n minus 1, plus a1, 2 to the n minus 2. And then all the way down to a n minus 1 times 2 to the 0. OK, and so now let's look at the bn minus 2 term. So we're summing over bn minus 2. And we have omega to the so now we're starting with a 1, and then 2 to the n minus 1. And a 2, 2 to the n minus 2. And now we don't go all the way down to this term, right? Because bn minus 2 doesn't appear here. We have to go to the 2 to the first power term. So we get n minus 1 times 2 to the first. And that's get bn minus 2 here. And so we keep doing this. And then, of course, we get all the way down to the b0 term. The b0 term just has a n minus 1, 2 to the n minus 1. That's the only, it doesn't appear here. It only appears here. OK? Everyone good so far? OK, are there any questions so far? I want to make sure, because this is one of the harder steps, and the next step is, well, the next few steps are the kind of the key ones. OK, I haven't really done anything non-trivial so far. I've just kind of written everything out in a very particular way in order to make it clearer what we're going to do next. OK, so now let's look at one of these terms in the middle. So this is going to be the Bn minus I term. OK, so it looks like sum over Bn minus I, and then omega to something, Bn minus I. And what is that something? So that something is, I mean, you can see this pattern here. It's definitely going to be a sum of the a's with powers of 2. But which a's and which powers of 2? Well, when we have n minus I, we're starting with n minus 1, we start with a0. With n minus 2, we start with a1. So with n minus I, we're starting with I minus 1. And the power of 2 that we get with that is always n minus 1 for the first term, right? And then we're adding up some more things that go from j greater than I minus 1, so the greater than or equal to I. And they go all the way to an minus 1. We always have an minus 1 here. And then what do we have? We have aj. That's the appropriate thing here. And the power of 2 goes down by the same amount. So it's n minus 1 minus 1 if j is equal to I, and minus more than that if j is greater than I. So let's make this n minus 2 minus j minus I. Right? So every time we increase j, we're decreasing the power of 2 by 1. Increase j by 1, we decrease this power of 2 by 1. OK? So this is the exponent of omega that appears in this term. OK, so let's analyze this. So you see the a's that appear here are, so we're doing the Bn minus I. So it's the thing that's in the I. So the very first term is Bn minus 1, right? That's when I equals 1. And the last term is b0. So that's when I is equal to n. So we're going from I equals 1 to n. And so the first bit is I equals 1, which originally was a0. Right? So if you kind of line up, and I guess I can do that now. So going in, we have a0. Sorry, we have a0, a1, a2, all the way down to an minus 1. And going out, and hopefully this is enough space, we're going to have coming out n minus 1, n minus 2, n minus 3, ... down to b0. And in particular, in the middle here somewhere, we have Bn minus I. And at that corresponding point here, we had I minus 1. That's the point I want to make right now. OK? So the thing Bn minus I is the same line that had I minus 1 at the input. So this term here is giving us a phase that depends only on the input value of that qubit. Right? These ones here depend on j greater than or equal to I. So they're things that are further down. OK? So this phase only depends, if you look at this output line Bn minus I, it only depends on that line coming in and the lines below it. Sorry, the lines above it. It's no, wait. Yes, lines below it. That's right. OK? The way I've organized this. OK, so in particular, let's look at this term here. So what do we get from that? We get an omega to the ai minus 1, 2 to the n minus 1. But omega, remember, is e to the 2 pi I over 2 to the n. And so this 2 to the n minus 1 mostly cancels that 2 to the n. So this is actually e to the 2 pi I over 2 to the ai minus 1, which is minus 1 to the ai minus 1. OK? So this is just saying, and this is a multiplicative factor because it's a sum in the exponent. So this is saying we should, for this particular qubit, we should have a phase of minus 1 if the input qubit was 1, and it should be a phase of plus 1 if the input qubit was 0. OK? Sorry, I think I missed something. I did, yes. Sorry, when I was expanding this, this is supposed to be a times b, right? So I just had the a terms here. So I'm supposed to have also a b n minus 1 here in the exponent, and a b n minus 2 here, and a b 0 here. And so this thing is has a b n minus I. And so, sorry, so this then is b n minus I and b n minus I, b n minus I. So, so sorry, it's not whether it's not just whether a is 0 or 1. It's if both a and b are 1 that we get the minus sign, right? And that's what you get out of a Hadamard transform. Right? If you do a Hadamard transform on that qubit, it will give you 0 plus 1, which is what we want. We want a sum here over all possible values. If the input qubit was 0, and it'll give you 0 minus 1. So there'll be the minus phase for the 1 term if the input qubit was 1. OK? So that's what we're going to do. We're going to do a Hadamard on every one of these qubits. Okay. I'm going to do those later. Because I'm not done, of course. I still have to do these other phases. OK? And those phases, remember, depend not just on this one line, but on this line and the lines below it. And the thing is that they have this factor of b n minus I. So I want their value after the Hadamard. That's when I get the b out. And then I want to multiply it by the a value for the lower line. So I want to do that before the Hadamard for those lines. OK? And then I just want to do a phase rotation of the appropriate angle, right? So for the one connecting adjacent lines here, I want to do a phase rotation by omega to the 2 to the n minus 2, right? Which is a pi over 2 phase rotation. But it's controlled on both of these qubits being 1 at this point. Sorry, it's going to be hard. I know it's going to be hard to see these numbers from the other side of the room. But and then I want to do one between this and this. And now it's r pi over 4. And we keep on doing these all the way down to the bottom. And we get an r pi over 2 to the n minus 1. OK? And this gives us exactly what we want for the b n minus 1 term up there. So we're done with the b n minus 1 term. And that line doesn't appear again, right? Because now, in order to get the phases right for these ones, we only need the ones below. OK? And so now we're ready to do the Hadamard on the second qubit. And then we do the same kinds of controlled phase rotations. And again, things that differ by 1, we're going to do an r pi over 2. So before it was pi over 4 because it differed by 2. Now it differs by 1 space. And the next one will be pi over 4. And then all the way down to the bottom, where we do this r pi over 2 to the n minus 2. OK? So far, so good? And then for this one, we do the Hadamard, and then we do the controlled whatevers all the way down to the bottom, where we're doing the r pi over 2 to the n minus 3. And we're done with this one. And then so on and so forth. And then finally, we get to the last qubit. And the last qubit is only interacting with itself. We only have that one term. And so we just have to do a Hadamard here. OK? So maybe, yeah, I'll give you a minute or two to think about that.
Why do you need the phase rotation thing?
Oh, yeah, OK. So, so what I'm doing is I want to do each of these terms in the sum, right? So I have omega to this thing times times b. And so I want to, so I'm going to take that omega to the sum and make a product of omega to individual things. So I want to replicate each of those phase terms. And so this first phase term comes from the Hadamard. And then each of the other terms comes from these controlled phase rotations, because they're all the form of aj times b n minus I. So I need something that depends on the j plus first line and the ith line. OK? So each of these gates corresponds to one term here in one of those things. OK? Are there any other questions? Yeah?
Why we don't uncompute the phases when we apply the Hadamard again?
Sorry, do you mean we would like to uncompute the phases, or?
In order to have the same, because in the first.
Yeah. So so it's important that these phase things. So what happens after, like, say this step? What do we have? Well, so this phase, I mean, the phase is not like associated to a specific qubit, right? It's a general phase that goes out front. And so what states do we have at this point? Well, we have b0, or sorry, bn minus 1 here, and a1, a2 through an minus 1 here. And what's the phase of that? And we have, some. We're originally starting with sum over different a's, but let's ignore that. We still have that sum. And we have sum over bn minus 1, because the Hadamard did that. And then within each of those terms in the sum, we have this ket that's b0, sorry, bn minus 1, a1, et cetera. And what's the phase of that particular ket? Well, it's this one up here. OK? So this is giving us exactly the phase that we want. We have no reason to uncompute it. We don't want to get rid of it.
Yeah, but my question was, like, when you apply the r pi over 2 after a1, after that you're going to get the phase on a1, right?
Yeah, that's what I'm saying, is that it's not a phase on a1. It's a phase on this whole thing. It's phase you can't localize to a single qubit, right? Because I mean, just look at the formalism, right? It's a phase here, but then the ket is over there, right? It's the whole ket. Yeah, and in particular, I mean, the phase here, we're applying a phase that depends on this state. And so that's the sense in which it has to act on this qubit. But it also depends on this state, of course. But then it just kind of sits in front. That's the way tensor product works. Yeah.
It's just you just organize it such that the phases, you just wrote the phases with the corresponding ket, but they're.
Yeah, that's right. I did at that point because those are the things that they depend on. And that's one of the two things that they depend on. Okay, so now, again, let's count how many gates we needed here. So this first thing involved, well, one Hadamard transform and n-1 controlled phase gates. So that was n steps, n gates. And the second thing, well, again, it's one Hadamard and n-2 phase gates, so it's n-1. And then the third one involved n-2, all the way down to 1. And so this is, of course, O of n squared. Okay? So the Fourier transform, even though it's kind of the really non-trivial quantum aspect of this algorithm, is actually much smaller than the modular exponentiation. That takes up more gates. Okay? So this is kind of finishing the breakdown of the quantum circuits in the algorithm. So now I'm going to move on to talk about that case where R does not divide 2 to the n. So if there's questions on the circuits, now would be a good time. Okay. Okay, so what happens when R does not divide 2 to the n? So, so remember what happened at the point where we're measuring the ancilla register up there. Right? At that point, we had a superposition in the kind of the idealized case. We had a superposition over A0 plus A0R plus A02R and so on. So it was, and that's still true, right? Because it's still the case that we're going to have some value A0, and we're going to have A0 plus R in that term, and A0 plus 2R. And so on. But the thing that's different is when R divides 2 to the n, when we get, I mean, depends where we put A0, but at some point, we're going to kind of wrap around. We're doing this mod 2 to the n. And when we wrap around, in the case where it divided, we got exactly back to where we started. If A0 was the smallest one, we get exactly back to A0. But in the case where R does not divide 2 to the n, we don't. Okay? So that means that it's still basically a periodic thing here, where all of these have R, except in one place. Right? These are R, and this is something else. Okay? And the Fourier transform is pretty robust against that kind of thing. Right? It's a function that's almost periodic. So clearly, it has a large component of R in its period. But the other problem is that this Fourier transform we're doing from integers to integers. Well, from numbers mod 2 to the n to numbers mod 2 to the n. And 2 to the n over r is no longer an integer. So that peak, that biggest peak in the Fourier transform, well, they're multiples of 2 to the n over r, those are not going to appear at integers. So what's going to happen after the Fourier transform is we don't get this, but we get, we don't get, and so in the idealized case, we got very sharp peaks at multiples of 2 to the n over r. In this case, we're going to get something that's pretty sharp, but not perfect. OK? And this one's going to be kind of roughly 2 to the n over r. But the real kind of peak will not be there because it's not an integer. So it's going to be between two numbers. So we'll get the floor of 2 to the n over r and the ceiling of 2 to the n over r will be our biggest values. And then it'll be pretty sharply peaked here. And this is going to be roughly 2 times that, and 3 times that, and so on. OK? And just how sharp and narrow these peaks are will depend on this little n relative to big N. And so it turns out that if we pick 2 to the little n to be roughly n squared, so now little n is 2 log big N, we get sufficiently narrow peaks so that the measurement outcome at the end of the quantum part of the algorithm is going to be pretty close to some multiple of 2 to the n over r with sufficiently high probability. And I don't want to get into exactly what it means to be sufficiently close. But the bottom line is that when you do all the rest of the classical post-processing, that with some at least constant probability, you'll be able to actually deduce C over R. OK, and so how do we do that? So in the idealized case, C over R was just some C2 to the n over R was just some integer, and we could do this a couple of times and take the GCD to get rid of the C's and get actually 2 to the n over r, and from that r. But now that doesn't work anymore. These are not integers. They're just kind of some kind of rational number. And the fact that it's rational is important. So so that kind of narrows down the possibilities. And we know, moreover, that that the thing that we're trying to get is also rational. And so it turns out that using something called the continued fraction expansion, which you may or may not have seen before, we can figure these out. So what we're going to do, b over 2 to the n is a thing that we know because we measured b. And so we can write this in terms of a continued fraction expansion like this. Where the C's are integers, OK? And so this is straightforward to do, right? You just say b over 2 to the n. Well, I guess b is going to be less than 2 to the n. So C0 is probably going to be 0. So we have 1 over something. And so we take 1 over that and say, well, what's the integer part of it? That's C1. And then the fractional part, we take 1 over that and say, what's the integer part of that? That's C2, and so on. And so because b over 2 to the n is rational, this thing terminates at some point. it turns out, and so C over R is rational as well. So it also has a continued fraction expansion. And it turns out that if these two things are sufficiently close together, and that's kind of what I wanted here, that the continued fraction expansion for C over R is also going to look very similar. It's going to have exactly the same terms up to some point. And it turns out that this one terminates but ends earlier. And that's the only difference in this continued fraction expansion from this one. Up to the point where it ends, all the terms are the same. OK? So what that means in practice is what we do is we take b over 2 to the n, we write the continued fraction expansion, and we try truncating at various points to see what works. OK? And again, you have to do Shor's algorithm, do the quantum subroutine a few times in order to get some different values of C. But you try that, and you try truncating each of those things, and see which ones can be common multiples of the same thing. And once you do that, you've gotten a pretty good guess at what 1 over R is. You calculate R, and then you go through the stuff that we talked about yesterday to turn that into factors. And then, because there's some uncertainty in all this step, it's probably a good idea to divide that factor into your big number n to see if it really is a factor. And if it is, then you're definitely done, right? Because all this other stuff is irrelevant. Once you actually have a factor, you can easily check that and see that it's right. But the thing is that if you guys had to guess factors, there's too many possibilities. So this is basically narrowing down the guesses to a very small set of possibilities that you can check easily. OK? So all of this adds some additional overhead, but it doesn't change the asymptotic scaling. They're just like relatively small factors, constant, maybe even constant factors. You get it with constant probability. OK? So the asymptotic scaling of Shor's algorithm is set by the modular exponentiation. And in the kind of the simplest multiplication case, it's order log n cubed. OK? So are there any questions on Shor's algorithm? Yeah.
So the modular exponentiation it's kind of a classical thing.
Yeah, I mean it's a completely classical thing, but we're doing it, remember, on the quantum circuitry because we need to do it on superpositions.
So I guess my question is that the point is that this is something that is efficient on a quantum computer. Is that so?
Well, the modular exponentiation. So, like if you're doing RSA, you also have to do a modular exponentiation, right, to do the encryption and the decryption. And it takes this. I mean, it takes the same number of steps on the classical computer and the quantum computer, maybe up to a factor of 2 or something for erasing scratch bits. And that efficiency, the efficiency is, again, using simplest multiplication, it's log of the number of bits and number that you're doing. So that's our criterion for being efficient, that it's polynomial in the size of the input. So yeah, yes, it's efficient. Any other questions? OK. I don't think it makes sense to start a new topic now. But tomorrow we're going to talk about Grover's algorithm, which is, in its standard formulation, it's a black box algorithm for finding, I mean, I mentioned it earlier, for finding a single one input, single input that gives one output out of a very long list. But it's really useful for a wide variety of circuits. Basically, anything where you need to try a bunch of things and say, oh, this one finally worked. You can use Grover's algorithm to speed it up. And Grover's algorithm is different from Shor's algorithm. Shor's algorithm if you compare to the best classical algorithm, is an exponential speedup, right? The best algorithms there were sub-exponential, super polynomial. And this quantum algorithm is polynomial. Grover's algorithm just gives us a square root speedup. It takes n, some big N number of possible inputs, down to about square root of n possible things that we have to try. But when big N is quite large, that can be quite a substantial amount. And given that it's widely applicable, it's still an important algorithm. OK, so that's what we'll do tomorrow.